Hey there, everybody. Let's see. Hold on. I got to figure out where I want to be. All right. So this graph we were talking about the other day, and I hope that even though you didn't actually see this happening, I hope that you are good with the fact that this right here is ice melting. And while the ice was melting, again, this is a beaker of ice on a Bunsen burner flame, on a ring stand, Bunsen burner flame. Ice was melting. Temperature was not really going up. Then once all the ice melted, it took off like a rocket and the water heated up really quickly. And then it got to the boiling temp, which we can see here, and the temperature stopped going up altogether because water in liquid form can't be hotter than 100 Celsius, or again, the boiling temp, unless you put it under pressure. If you put it in a pressure cooker, like an Instapot, that allows the pressure inside this container to increase, which keeps the liquid in liquid form without letting it boil and vaporize. So anyway, you were supposed to have sketched this on this. Yes. Now I added some things to this. This is what you wrote down the other day, or at least you should have, because it was in the notes that I had added. During the melting, all right, during the melting, all the while the beaker of ice was on the Bunsen burner flame, the particles were gaining energy. Were they getting faster? They were not getting faster. How do we know they weren't getting faster? Because what wasn't changing? The temperature was not changing. They were not getting hotter. Therefore, they were not getting faster while the ice was melting. I hope you're understanding this. The idea that we're saying no temperature change during a phase change, we're saying that while the ice is melting, the temperature cannot go up. So what is all the energy that they're gaining? Where is it going? It is breaking the structure and allowing the particles to gain some freedom. Okay, that's where the energy is going. The energy is not making the particles faster, it's giving them freedom. It's breaking the structure of the particles that can only shake and vibrate back and forth in a solid. That structure is breaking apart, and that costs energy. So they're not getting faster, they're gaining some freedom. Once all that's done and the ice is melted, then the liquid water can heat up. So are the particles gaining energy here? Yes. Remember, it's on the Bunsen burner flame this whole time. The particles are gaining energy the whole time. But the gaining of energy now, during this section, they're getting faster. They are getting faster because it's getting hotter. Look what the temperature is doing. The temperature is rising from 0 up to 100 in the middle section. So at that point, all of the energy the particles are gaining is making them faster. And it's doing it pretty quickly. Then they reach the boiling point where the water temp cannot go up anymore. Are the particles still gaining energy? Yes, the beaker of water that's boiling now is still on the flame. The particles are still gaining energy. They're not getting faster. They're not getting hotter because the temperature can't go up anymore because a phase change is occurring. What are the particles gaining with all this energy that they're getting? They're gaining total freedom. Total freedom is being gained. All right? So, I hope you're seeing here, as the time went on, there's never a time on this graph where the particles aren't gaining energy. In other words, they're always gaining energy. The particles are always gaining energy on this graph during the process of ice melting, water heating, and then water boiling. They're gaining energy the whole time. Sometimes, like during a phase change, the energy they're gaining is giving them freedom for the structure of the solid falling apart. Or, in the case of boiling, it's giving the liquid particles total freedom where they get huge separation. They can move around anywhere they want. Total freedom. That costs something, and it costs a bunch of energy. They didn't get faster. They got total freedom. And of course, in the middle here, that's when the energy that they're gaining is making them faster. That's during the heat up, not a phase change. The water's just still water, still liquid the whole time, but getting hotter. So again, during phase changes, the temperature cannot change. All that's happening is they're gaining and losing energy to change their arrangement and how much freedom they have. I hope that makes sense. Which means that when we look at, I got to look at this other slide here. When we look at this right here, when we look at all these different phase changes here, the 6 different phase changes, so sublimation, evaporation, melting, freezing, condensation, and deposition, all 6 of those phase changes, the temperature can't change during any of them. Temperature can't change. During evaporation, the temperature can't change. After evaporation has happened, once the stuff is a gas, then the particles can speed up. And after the gases become a liquid through condensation, after that happens, the particles can slow down. But while it's actually happening, while the change is occurring, they cannot speed up or slow down. All they do is either gain freedom or lose freedom because of the energy that they're gaining and losing. So again, when the particles are gaining energy on the left side here or losing energy on the right side, when they're gaining or losing, when they're gaining, it's because they're gaining freedom. And when they're losing energy, it's because they're losing freedom. I hope you're getting that. Not changing temperature, but gaining or losing freedom. Now, after this, let's see, I showed a couple demonstrations, which I'll actually take a separate video of 5th period. I'll grab my phone and I'll take a couple of short videos of those demonstrations so you can see those things happening. And let's see, so that will be coming, and I'll add that video to the post. So be looking for that. Now, at this point, if I were you, I would pause this video, and then go watch the last episode of the Eureka videos. I think it's episode 21. So watch the last episode of Eureka videos, and then come back to this, and then I'll talk about what was in that last video. So do that now, and then come back, and then finish this. I'm just going to keep going, but you need to stop this, look at the other one, and then come back. Now, hopefully you did that. And so here is the deal with that. Let's see. Okay. They said in that video that temperature is based on the speed of the particle, and that heat, they called it heat, is based on both the speed of the particle and the mass. I rearranged, I called it something a little different. So here's what I say. I say that the temperature is based on particle speed, that's true. Temperature is based on particle speed. Thermal energy, though, I don't call it heat. Scientifically, we usually don't call it heat. We call it thermal energy. It's like the scientific name for heat. Heat or heat energy or thermal energy. That depends on particles, not just particle speed, but also how many particles there are. The number of particles and how fast they are is what we call energy. Temperature is just how fast they are. Now, what exactly, who cares? What's the deal? Why does that matter? Well, let's think about this. If you are, let's say you're a coffee drinker, okay? You love coffee. And let's say you went through the drive-through, maybe McDonald's, you got yourself a coffee. And let's say it's, about 150 degrees. I mean, we're talking hot coffee. Let me write that up here. What in the world? Come on now. Oh, please. Are you kidding me? Oh boy, this is not responding. Oh boy. Things are looking. Oh, it finally responded. 100. Oh, please tell me. Okay, 150 degrees. Now, let's see. You are sitting there with 150 degree coffee. Now, again, folks, that's over 50 degrees hotter than your body temperature. And that is hot enough to actually scald you and damage your skin. Okay. Now, obviously, it's not boiling, but it's hot enough to do damage to you. You've got a cup of coffee. You got yourself a cup of coffee that's 150 degrees Fahrenheit. And then let's say I have a little pot of water that's boiling, and I'm going to take a teaspoon out of there. And here's what you're going to have a choice. Either I'm going to take one little teaspoon of boiling water and pour it on your hand, or I'm going to take that entire cup of 150 degree coffee and I'm going to pour it on your hand. Which one do you think is going to do more damage or be a little more uncomfortable? I would say that the 150 degree coffee is probably going to do more damage to your skin than the 212 degree water. Why? Because it's only a teaspoon. Like, a teaspoon is not very much. You put that teaspoon on you, yeah, it's going to hurt. But it's going to cool down really quickly because there's not much of it. Very small amount. If you pour that whole cup of coffee, 150 degree coffee, all over your hand, that is going to do some damage. Okay. So what the coffee particles lack in particle speed, they're making up for by how many there are. So the 150 degree cup of coffee has way more energy in it than a teaspoon of 212 degree water. I hope that makes sense. So when you're talking about energy in the substance, it's not just about how fast the particles are, it's about how many there are. One other thing to kind of reinforce this and think about this, when I posted, let's see, what was it? Oh, it was this. All right, so this assignment right here, this question, it says you decide to boil water to cook noodles. So we said the behavior of the water molecules changes in terms of the pan is on the burner is on. Obviously, the pan's getting hot, the water's getting hot, which means the particles are moving faster. So we have faster particles, which means the temp's going up. Yeah, they're moving faster. They're getting a little bit further apart. So the water is expanding a little bit, but you can't really notice when you look at the pan. It's not like the water swells up huge. The water gets a little bit bigger because the particles got a little bit further apart, tiny amounts. But the particles got faster, and they finally got to boiling temperature, and then you can throw your noodles in. And so the question for B here was, what changes if there's more water in the pan? And you all said nothing changes. The particles are still gaining energy. They're still getting faster. They're still getting a little bit further apart, and then eventually they reach boiling temperature. So that's all true. But then you also said that this was going to take what? With more water, that means there's more particles, and that means it's going to take longer, which means the burner has to give the pan of water more energy. Why? Because there's more particles. Well, aren't they both going to get to boiling temperature? Aren't both pans of water going to get to boiling temperature? Yes. but the one with more particles is going to take longer because it requires more energy because there's more particles. So that's what we're saying here. When we're looking at the thermal energy versus temperature, thermal energy cares about how many particles there are and how fast they are, both. So I hope that makes sense. Now, we were talking about particle diagrams and how do you indicate, like in this case here, how do you indicate that this car in this cartoon is moving? Well, first period suggested, well, because you got these little lines of motion. You show these little motion lines on the back of the car, and that's how we can show that the car is moving in a cartoon when it's really just sitting there. But we're giving the illusion, that there's motion because we're showing, hey, there's like motion lines. That's typically how a cartoon would show that, or a sketch like this would show that the thing is moving. And so we haven't drawn a single particle diagram, and it's been like four class periods, and we haven't even drawn a single particle diagram. And so I apologize for that. We probably should have been drawing some particle diagrams along the way, but we didn't. So these little motion lines, I hate to call them this, but this is what the people that came up with this curriculum, that's what they call it. They call them whooshies. I don't even know what that means, but that's what we call them. They're whooshies. The whooshies are the motion lines that show that this car is moving. And that's what we're going to use on our particle diagrams to show that the particles in the diagram are moving. Now, I asked everybody, I should use, hold on, I'm going to put a screen on this thing. And then I'm going to, oh boy, then I'm going to start dragging it down here. Oh gosh, this is taking too long. Dragging it down, dragging it down. Dragging it down, dragging it down. Oh my gosh, I apologize. This is ridiculous. Oh my gosh. I should have done this at the beginning. Okay, so here's what I suggested. I said, hey, if we want to draw water as a solid, as ice, how would we draw that as a particle diagram? And so this is what I did. I drew this. Oh no. Oh gosh. Hold on. Oh, I don't want. Oh, geez. There we go. This is how I drew the particles. Okay. They're in a structure. They're in an arranged pattern, like the way solid particles are. And look at the tiny little whooshies, tiny little lines of motion, little like one or two on each particle. They're not moving very fast because this is cold. It's ice. Okay. Then I said, okay, as a liquid, let's say it's hot. Let's say it's hot water. So I have hot water. How is that going to look differently as a liquid than it did as a solid? Well, liquid particles lose their what? Particles as a liquid lose their structure. They lose their structure. And so that might, oh gosh, that might look like this. Why is this here? I don't want that there. I don't want that here. Why is that here? So they lose their structure. These are kind of random. And notice I put more lines of motion on it. They're a little longer as well, but I put more of it. So now there are 2 or 3 lines of motion because it's hot water. So cold particles like ice, they don't have much movement, and so they have very small lines of motion, not much motion at all. These water particles that are hot now have way more movement. And notice they're totally random. Their spacing is about the same as it was over here. They're still pretty close together, but they're not structurally organized. Okay. Then I asked, hey, what do you do about the gas particles? Let's say we even have a hotter vapor now. So now this liquid here, it boiled and it produced a vapor, a very hot vapor. It was suggested that these particles are very far apart and they're moving way faster now even than before. Totally random. And so now I've got them really far apart, 3 or 4 lines of motion now. So they're flying around everywhere, completely random, very fast, bouncing all over every place. Okay. So this is how you might see particle diagrams that would show the difference between solids and liquids and gases. And not only that, cold solids, hot liquids, and then even hotter vapor. Now, what if the solid and the liquid are about the same temperature? Well, then the whooshy thing wouldn't be that big. Like, you wouldn't draw as many or as long of whooshies. If this was really cold water, then it's not going to be that much warmer than the ice if it's really cold water. And so you may not have that much difference in how much speed they have, but their structure would be apart. They'd no longer be in an organized structure, and they would have the ability to kind of slip and slide past each other. So again, how many whooshies or lines of motion you draw is going to depend on how hot the stuff is. So because I've got a cold sample of solid and a hot sample of liquid and an even hotter sample of gas, that's just kind of the progression that I chose. That's not to say that all gases are hotter than all liquids, because obviously they aren't. So, I mean, if you look at, especially in the wintertime, as Lake Erie or even the Maumee River gets colder, like, I'm not sure what the river temperature is right now, but it's got to be pretty cold. And today it's supposed to be pretty warm, air temp. So the water vapor in the air is actually going to be warmer than the liquid temp. However, the other day, when it was 28 degrees when we woke up and came to school on Monday, I think it was, 28 degree temperature air means that the water vapor in the air was slower than the maybe 40 or 50 degree river temperature, probably 50 degree. So at that point, the gas particles were actually slower than the liquid particles. So it's not that gas particles are always faster than liquid particles, because they aren't. Remember, how fast they are, it depends on the temperature of the particles of the substance. All right. Now, the last thing I left everybody with that we're going to talk about on the next class, which is also when the test is going to happen. We're going to finish talking about all this stuff, and then you're going to take the test. This is the question I wanted to have answered. I said, I'm in the way, I think. I wanted you all to sketch a particle diagram of two different thermometers, one in freezing water, one in boiling water. And I want you to show, like, either the alcohol or the mercury, whatever's in these thermometers, I want you to show what that liquid would look like in the thermometer itself if it was in freezing water versus if it was in boiling water. Like, how is that going to change the particle diagram if you draw the alcohol or mercury as particles in these, like, thermometer pictures? How is the freezing one going to look different than the boiling one? So that's what I want you to do for the next class. We'll talk about that. I'm also going to post another thing. It's actually called the Changes of State worksheet. I'm going to post that as well, because we will talk about some things on that as well before you take the test. So at this point, you better know what the phase changes are, the changes of state. There's 6 of them, remember? 6 of them. Oh, get my hand in. Oh boy, there's 6. 6 of them. 6. Remember, deposition, sublimation, melting, freezing, evaporation, condensation. 6 of them. And you need to know what the particle behavior is like in solids, liquids, and gases. You need to understand the difference between temperature and thermal energy. So there are several things you need to make sure you know and understand for this test that's coming up. So again, this video, hopefully you got that. The Eureka video, hopefully you already watched that. Hopefully you wrote all these notes down. Hopefully you're writing this down as an assignment. And then I'll see you hopefully on the next situation. Now, there will be another video. I'm telling you that now, even though by the time I post this one, the other one will probably already be recorded and uploaded as well. So I guess there are several videos for today that you should watch all of them. Okay, I think that's it. I think I'm finally done. We'll see you guys later. Take care of yourselves.